Hello, this is Khaleel Hussain Mohammed. I'm here to present the weighted graph presentation. So the agenda of this presentation is Introduction to Weighted Graph, Advanced Concepts of Weighted Graph and MST, which is basically Minimum Spanning Tree, the shortest path algorithm, network flow problems, real-world applications, questions, and conclusions. So we'll start with Introduction to Weighted Graphs. The introduction of weighted graph is a weighted graph is a type of graph where each edge is assigned a numerical value called a weight. This weight represents some cost, distance, or capacity associated with that edge. For example, road networks, communication networks. The road network's weight might represent the distance between two cities, but the communication network weight could represent the bandwidth and latency between two computers. So, the importance of weighted graph. The weighted graphs are crucial for solving many real-world problems where you need to find optimal solutions based on the weights of the edges. Like for instance, they help in finding the shortest path between locations or like optimizing network flows for data or resources, designing efficient transportation and communication systems as well. So we'll go to the next slide. In this slide, we will learn about the key concept and definition of weighted graph. The first is vertices and edges. It is like a basic components of a graph. Vertices or nodes represent entities or points in the graph, and edges represent connections between these vertices. In a weighted graph, each edge has an associated weight. And the weighted paths. The weighted paths are sum of weights along a path. A path is a sequence of edges connecting two vertices. The weight of a path is the sum of the weights of the edges in the path. And the graph representation. The graph representation is like adjacency matrix. Adjacency matrix is a 2D array where each element ij represents the weight of the edge from vertex I to vertex j. And the adjacency list is a list where each vertex has a sublist of edges with each edge represented by the adjacent vertex and the weight. Now comes to the last point, directed versus undirected graphs. Edges have a direction, example one-way street, and undirected graphs are like edges do not have a direction, example two-way streets. So the direction of edges matters in some problems, no, but not in all problems. The next slide is MST, which is basically minimum spanning tree. MST is a subset of the edges in a weighted graph that connects all vertices together with the minimum possible total edge weight and no cycles. The algorithm for MST. There is a Prim's algorithm. Uh, it is like a greedy algorithm that starts from an arbitrary vertex and grows the MST one edge at a time. And there are steps for it, like first initialization, grow the tree, termination, properties, and examples. So initialization is like a start from a vertex and mark it as visited. And then grow the tree, select the smallest edge connecting the visited vertex to an unvisited vertex. The termination, continue adding edges until all verticals are included in the MST. Properties, best for dense graph with many edges. And examples are like imagine you are building a road network that connects all cities with the least cost. This is a Prim's algorithm and Kruskal's algorithm. The Kruskal algorithm is a greedy algorithm that adds edges in increasing order of weight while avoiding cycles. Uh, Initialization, sort edges, build MST, termination, properties, an example, etc. So the initialization start with all vertices and separate components. Sort edges, list all edges by weight from lowest to highest. And building MST is like adding edges to MST if they don't create a cycle. So termination is stop when you have edges where number of vertices. The properties efficient for graph with many edges and when edges are given a list. For example, constructing a network of cable where you want to minimize the total length. This is like a definition of Kruskal's algorithm. And the last is Borůvka's algorithm. It is a greedy algorithm that finds an MST by connecting components with the smallest edges. So it treat with each vertex as a separate component in each phase. Find the smallest edge from each component to another component and add it to the MST. Repeat until there is only one component remaining and efficient for large graphs and in parallel computing. For example, building a network where you progressively connect clusters of nodes using the smallest possible edges. We'll go to the next slide now. Uh, Definition of shortest path algorithms. This is a Prim's algorithm. These algorithms find the path with minimum total weight from a source vertex to a destination vertex in a weighted graph. An initialization is like start with an arbitrary vertex, mark it as visited, grow the tree, the termination, everything is like same. Always build the MST incrementally, efficient for dense graphs with a large number of edges. This algorithm find the path with the minimum total weight from a source vertex and definition of vertex in weighted graph. And we'll go to the next slide. Kruskal's algorithms. The Kruskal algorithm is a greedy algorithm used to find minimum spanning trees, MST, for a connected weighted graph. There are some steps for that, like initialization and sorting edges, building MST, termination properties, which involves a lot of steps, like start with all verticals as a separate components, arrange all the edges in non-decreasing order of the weight. And building MST is like iteratively add the smallest edge to that doesn't form a cycle or MST. Merging component as edges are added. So it is efficient for graphs with large number of edges, and it also works well with edge list of disjoint sets. This is like Kruskal's algorithm definition. So this is Borůvka's algorithm. We have talked about this. Now there is a shortest path algorithms. These algorithms find the path with the minimum total weight from a source vertex to a destination vertex in a weighted graph. And there are algorithms for shortest paths, like Dijkstra's algorithm. Uh, the Dijkstra's algorithm finds the shortest path from a single source vertex to all other verticals in a graph with non-negative weights. And the steps of this is like initialization, relax edges, repeat properties, and for example, finding the shortest route on a map. So first, the initialization is like setting the distance to the source vertex to 0 and all other distance to infinity. Relax edges, update the distance to neighboring vertices, continue until all vertices have a shortest distance determined. Efficient is for graphs with non-negative weights and many edges. And Bellman-Ford's algorithm. The Bellman algorithm handles graph with negative weights. It finds the shortest path from a single source to all other vertices, handling graphs with negative weights. So set the distance to four. The Bellman-Ford algorithm sets the distance to the source to 0 and all others are infinity. Update distances for all edges and detect negative weight cycles. It can handle negative weights but slower than Dijkstra's. For example, finding the shortest path in a financial network where some paths might have negative cost. Uh, Algorithm. Algorithm is an extension of Dijkstra's algorithm that uses heuristics to improve search efficiency. It starts from the sources and use heuristics to guide the search towards the goal. Heuristic function. It combines the cost to reach a vertex and estimate of the cost of the goal. Properties like efficient for pathfinding problems, where you can estimate the remaining distance. And for example, GPS navigation systems where you use both the actual distance and a heuristics to find the shortest path. So nowadays, everybody uses the GPS system to navigate. It's easier for to travel and everything. So the Johnson's algorithm is like compute this shortest path between all pair of vertices in a graph with both positive and negative weights. It add a new vertex to reweight the graph. Run Dijkstra's algorithm for each vertex is the source, efficient for the sparse graphs. For example, it's like a traffic analyzing where you need to find the shortest routes between multiple locations. So this is all about the shortest path algorithms. Now we'll move on to next slide, network flow problems. These problems involve finding the maximum flow from a source node to sink node in a flow network where edges have capacities. Algorithm for network flows is the Edmonds-Karp algorithm, an implementation of the Ford uh, Fulkerson's using BFS. BFS is like breadth for search. The initialization is like we'll start with set the flow to 0, use BFS to find paths from sources to sink, increase flow along the path found, ensures the maximum flow solution. For example, maximum data transfer in a network of servers. Push-Relabel algorithms, a more advanced algorithm for network flow problems, efficient for very large networks. So initialization set the initial flow and vertex heights, increase the push flow is like increase the flow from vertices to with excess flow. Reliable vertices adjust heights to find new paths, efficient for very large networks. And for examples, managing traffic in a road network with many intersections. So this algorithm is really helpful in that scenarios. Applications. The applications of graph algorithm is like Dijkstra help find the best path for data packets across the internet and transportation network examples. These are the like practical examples and applications. So internet routing, transportation networks, logistics and supply chain, telecommunication, energy grids also. So algorithms is like Dijkstra help find the best path for data packet across the internet, and transportation network is algorithms help in planning optimal routes for public transportation, finding the shortest travel routes. So, and logistics and supply chain are used to manage distribution networks for goods, which will cost effective resource distribution. And the telecommunication is algorithm optimize bandwidth usage for different data streamers. So it is efficient bandwidth allocation. And the last is energy grids. Algorithms helps in balancing load and distributing energy efficiently. So it's a efficient distribution and load balancing grid. We'll move to the next slide. Interactive problem. Finding minimum spanning tree, MST. So vertices A, B, C, D, E, edges with weights represent connection and their cost. There are steps to find the MST. So the steps is like sort edges first. First, we need to arrange the edges by their weights. Then again, we have to initialize components. Start with each vertex as its own component, and then again we have to add edges, like adding the smallest edges that don't create cycles. And then complete MST. Continue adding edges until all vertices are connected. For example, starting with the edges sorted by weight, AC1, CE1, DE1, etc. And add edges too. So this is all about the weighted graphs. Uh, and in this presentation, we have learned about the weighted graphs, introduction and advanced concepts of weight, minimum spanning tree, what is MST, and we have learned about the algorithms, the shortest algorithm, Dijkstra's algorithm, Prim's algorithm, and network flow problems as well. So that's all about this weighted graph problems. Thank you.